Welcome to the deep dive. Today, we're taking a plunge into a really cutting-edge topic, multi-agent research systems. Now, this isn't just about making, smarter chatbots. It's really about how advanced AI models are being built to tackle those really complex, open-ended problems, the kind that go way beyond simple Q&A. Our mission for this deep dive, well, it's to unpack a brand new publication from Anthropic. They've given us this incredible look, really, at how they built their own multi-agent research system. Specifically, we're talking about their research feature, which uses multiple Claude agents working together. So we're going to pull out the core insights, try to understand the why and the how behind these architectures, and maybe uncover some surprising facts. Think of it as your shortcut, really, to understanding what might be the next frontier of AI.
Yeah, just to set the stage quickly, when we talk about a multi-agent system, just picture this. It's not just one, super powerful AI. Instead, you've got multiple AI agents, basically.
Mhm.
Large language models, LLMs, and they're working together autonomously. They use tools, they operate in this continuous loop. And this kind of collaborative approach, well, it definitely introduces new challenges, but wow, it also unlocks immense potential for what AI can actually do.
Okay, so let's dive into the why then. I mean, when you think about research, actual human research, it's inherently, well, it's unpredictable, isn't it? It's messy. You adapt as you go. How does an AI even start to tackle something so fluid?
So path dependent.
Yeah.
When you research, you don't just follow step A, B, C, you pivot based on what you find. You've hit on the core problem exactly.
Yeah.
That unpredictability, that dynamic nature. It's precisely why AI agents, and especially multi-agent systems, are so well suited for these kinds of tasks. A single linear AI pipeline. It just struggles with that dynamic adaptive process. The real genius here is that the system can operate autonomously over, many turns. It makes decisions about which paths to explore based on what it's finding along the way, just like a human researcher would.
So if that's the challenge, what's the sort of architectural breakthrough, the aha moments that lets them address it?
Well, the aha moment really comes down to two key design principles:
Yeah.
compression and separation of concerns. And compression, it's not just about efficiency. It's like this cognitive leap, condensing vast amounts of parallel exploration into insights the lead agent can actually use without getting overwhelmed. And separation of concerns, that's not just tidy programming. It's strategic. It helps fight against the biases or tunnel vision a single agent might have. It allows for these really independent, thorough deep dives. Each subagent gets its own context window, its own tools, its own prompts, its own sort of exploration path.
Right, so you get truly independent investigations happening at the same time.
Exactly. It avoids that path dependency where the first thing you find biases everything else.
If we zoom out a bit, it almost sounds like you're building an intelligent team, not just running a program.
That's a great way to put it. It connects directly to this bigger idea of collective intelligence. Think about human societies, right? We became exponentially more capable through coordination collaboration. Multi-agent systems are, in a way, a path to scale AI performance beyond what any single agent could do alone. Even a really smart agent hits limits by itself. Groups can just achieve much more.
Okay, we've talked architecture, but the proof is in the pudding, as they say. What kind of performance gains are we actually seeing? Is this like a small improvement or something really significant?
Oh, it's definitely significant. Their internal tests show these systems really shine on what they call breadth-first queries. Those are tasks where you absolutely need to explore multiple independent paths at once. And get this, a multi-agent system with Claude Opus 4 as the lead and Claude Sonnet 4 as the sub-agents, it outperformed a single Claude Opus 4 agent by, wait for it, 90.2%.
90%, wow,
Yeah.
it's huge.
It's massive. They gave an example, like identifying all the board members for IT companies in the S&P 500. The multi-agent system just broke it down, farmed it out to sub-agents, got the answers. The single agent, it struggled, doing slow, sequential searches.
Okay, so what's the secret sauce there? How do you get that kind of leap? Is it just more agents equal more smarts?
Well, it's a bit more nuanced. The real secret, interestingly, seems to boil down to spending enough tokens, the basic computational units for LLMs. In one of their analyses on a browsing task, token usage alone explained like 80% of the performance difference.
80%, just from tokens.
Yeah, which basically validates their architecture, right?
Yeah.
It's designed to effectively scale token usage by splitting the work across agents, each with its own context window, so you can just use more tokens effectively. And it's worth mentioning, too, the newer models, like Claude 4, they act as efficiency multipliers. So upgrading the model can actually give you a bigger performance boost than just throwing more tokens at an older model.
So it's smarter distribution of computational effort, essentially, more efficient and distributed intelligence. But okay, there's always a catch, right? What's the downside? This sounds computationally expensive.
You're absolutely right to ask that. There are trade-offs, and yes, these systems do burn through tokens fast. We're talking like typically around 15 times more tokens than a standard chat interaction.
15 times?
Yeah,
Ouch.
so that means, at least for now, they're really only economically viable for tasks where the value you get from that extra performance is high enough to justify the cost. You wouldn't use it to, ask about the weather.
Right. High value problems. And beyond cost, are there specific kinds of tasks where this multi-agent approach just isn't the right tool for the job?
Definitely. They're not ideal for tasks where every agent needs the exact same, constantly updated context,
Hmm.
or things with tons of dependencies between the steps. Think about most coding tasks, for example. The steps are often highly sequential and interdependent. LLM agents aren't quite there yet with that kind of real-time, intricate delegation. Where they really excel is heavy parallelization. Tasks where the information needed just won't fit in a single context window, and situations involving lots of complex tools.
Okay, that gives us a really clear picture of the why and the when. So now let's pull back the curtain a bit. How does this actually work under the hood? What's the structure?
The core architecture is often described as an orchestrator-worker pattern. It's a pretty intuitive idea, actually. Just imagine a lead agent, kind of like a project manager, coordinating everything. And then it delegates specific tasks out to specialized subagents, the workers.
Okay, so walk us through it. A user asks a question, then what?
Right, so the user query goes to the lead agent. The lead agent analyzes it, figures out a strategy, like a plan of attack, and then it spawns, creates multiple subagents to go off and explore different facets of the query in parallel. These subagents, they act like intelligent filters. They use tools like web search iteratively. Maybe they're looking for, say, AI agent companies relevant in 2025. They gather info. Then, once they've done their piece, they report their findings back to the lead agent. And the lead agent takes all those pieces and compiles the final answer.
That sounds way more dynamic than, say, standard retrieval augmented generation, RG, that we often talk about.
Oh, absolutely. That's a great point. Traditional RA often relies on static retrieval, right? You
Yeah.
grab some pre-indexed chunks of text based on the query. This multi-agent system, though, it's dynamically finding information, it's adapting based on intermediate results, it's analyzing things in this multi-step search process. It's much closer to active research and synthesis, not just retrieval.
Can you give us a bit more detail on the full workflow, like Anthropic's research feature specifically?
Sure. So when you give it a query, it spins up a lead researcher agent. This agent starts by planning its approach. Crucially, it saves this plan to memory. That's important for maintaining context, especially if the whole process needs more than the 200,000 token context window. It prevents things getting cut off. Then it creates specialized subagents, giving each one a specific research task. Each subagent goes off, does its web searches, looks at the results, decides if they're good, and sends its findings back. The lead researcher looks at what came back, synthesizes it, and decides, do we need more? If yes, it might create more subagents or maybe refine the strategy for the existing ones. Then, once it feels it has enough information, there's a final step. A dedicated citation agent goes through all the source documents and the draft report to make sure every claim is properly linked back to its source.
Okay, managing all that. It sounds like it could get complicated fast. The paper mentions this rapid growth and coordination complexity. What kind of maybe funny or frustrating failures did they run into early on, and how did they fix them?
Oh yeah, you can imagine. Early days must have been. Interesting. The paper mentions things like spawning 50 subagents for a really simple query, just overkill, or agents getting stuck in loops, searching endlessly for a source that just didn't exist, or even agents kind of distracting each other with too many updates.
Huh. Sounds like managing humans sometimes.
Exactly. And the fascinating part is that their main solution wasn't some complex algorithm. It was primarily prompt engineering, basically teaching the agents how to be better collaborators, how to work together effectively.
So prompting is like setting the rules of engagement for the team.
Precisely. And they shared some key principles they learned. One big one was think like your agents. They actually ran simulations, watched the agents work step by step. That immediately showed where things went wrong, like agents searching way too long, using bad search queries, picking the wrong tool for the job. Seeing it happen made it obvious what needed fixing.
That makes sense. See the failure? Fix the prompt.
Right. Another key thing was teaching the orchestrator how to delegate properly. Subagents need really clear goals. Clear objectives, specific output formats, guidance on which tools or sources to use, clear boundaries for their task. If you just told it vaguely, research the semiconductor shortage, you'd get chaos. Agents duplicating work or totally missing important aspects because the instructions weren't precise enough.
So clarity and delegation is paramount.
Absolutely. And also, scaling effort to query complexity. Agents don't automatically know if a question is simple or needs a deep dive, so they had to build scaling rules right into the prompts. Like, okay, simple fact check, that's maybe one agent, 3 to 10 tool calls. Complex research report. Okay, that might need more than 10 sub-agents, each with a clearly defined piece of the puzzle. This stops the system from, burning tons of tokens on easy questions.
Smart. Conserves resources.
Definitely. And of course, tool design and selection. This was critical. The way the agent interacts with its tools, the descriptions, the parameters, it's like the user interface for the AI. They had to give the agents clear rules, heuristics for using tools. Like, look at all your tools first, or prefer the specialized tool if available. Bad tool descriptions could send an agent completely off track.
Right, garbage in, garbage out even applies to tool descriptions for AI.
Exactly. And here's something I found pretty amazing. They actually managed to let the agents improve themselves. The Claude 4 models are apparently quite good at prompt engineering themselves. You could give it a prompt and explain how it failed, and it could often figure out why and suggest improvements to its own instructions.
Wow, the AI is debugging its own prompts.
Yeah. They even made a tool testing agent. You'd give it a tool with a bad description, it would try to use it, fail, and then rewrite the description to be clearer. And using those rewritten descriptions led to something like a 40% decrease in task completion time for future agents. The AI is literally teaching itself and its peers to be more efficient.
That's kind of mind-blowing. Self-improving systems in action.
It really is. They also prompted agents to start wide, then narrow down, just like good human researchers do. Initially, agents tended to jump to very specific searches too quickly. So they guided them, start broad, see what's out there, evaluate, then get more specific. And they use something called extended thinking mode. Think of it like a scratch pad for the AI. It lets both the lead and subagents kind of think out loud, plan their approach, weigh tool options, refine queries before acting. This really helped with following instructions correctly and just being more efficient overall.
Like showing your work in math class.
Kind of. And finally, a huge performance boost came from parallel tool calling. Early versions did searches one after another sequentially, and it was, as they put it, painfully slow.
Yeah.
So they introduced 2 layers of parallelism. First, the lead agent could spin up, say, 3 to 5 subagents to work in parallel. And second, each subagent could use maybe 3 or more tools simultaneously. That combination. It cut research time by up to 90% for complex queries.
90% again. Parallelism is clearly key.
Absolutely transformative for speed.
Okay, so summing up this whole section on how, it sounds like it's less about writing rigid code and much more about embedding good research habits, good heuristics into the prompts, along with safety rails and a really fast feedback loop.
That's a perfect summary. And good evaluations are absolutely essential for building reliable AI applications, agents included. But evaluating these multi-agent systems, it brings unique challenges. Like you said, unlike normal software, agents might take totally different paths to get to the same perfectly valid answer. So you can't just check if they followed specific steps 1, 2, 3. You need more flexible methods, focusing on whether they got the right outcome through a reasonable process.
So how do you measure success then? Especially when the output can be so varied, so free-form.
Well, they learned some practical lessons. First, start evaluating immediately, even with small samples. Especially early on, small changes in prompts or tools can have huge effects. They found that even testing with just 20 or so representative queries could show massive jumps, like success rates going from, say, 30% up to 80% after a change. So don't wait to build some giant evaluation set. Start small, start early.
Get that rapid feedback.
Exactly. Second, LLM as judge evaluation actually works pretty well if you set it up right. Since the output is often text or research report, for instance, using another LLM to grade it makes sense. They gave the LLM judge a clear rubric. Check factual accuracy, check citation accuracy, completeness, source quality, even tool efficiency. And this gave consistent enough pass-fail grades and scores, especially for tasks with relatively clear answers. It let them evaluate hundreds of outputs scalably.
Okay, so use AI to judge AI with a good rubric. But that can't catch everything, can it?
No, absolutely not. Which leads to the third point. Human evaluation is still crucial. You need humans to catch the things automation misses. Humans are great at finding those weird edge cases, hallucinated answers that sound plausible, subtle system failures, biases. For instance, human testers noticed early versions tended to favor, like SEO-optimized content farms over actual authoritative sources like academic papers.
Ah, the classic SEO problem.
Right, and that feedback led directly to them adding new heuristics about source quality into the prompts. So humans provide that essential sanity check and catch the nuances.
So you need both automated scale and human nuance. It's about understanding those emergent behaviors, how small tweaks can have unexpected ripple effects, and having the right evaluation mix to see and steer them.
Okay, let's shift gears a bit to the really practical side, actually building and running these things in the real world. You often hear that for AI agents, the last mile becomes most of the journey. Why is that especially true here? You mentioned errors compounding. Yeah, the engineering challenges are definitely significant. Think about it. Agents are stateful. They run for potentially long periods, remembering things across lots of steps, lots of tool calls. So if an error happens halfway through a long research task, you can't just tell the user, oops, start over. That's incredibly frustrating and expensive in terms of tokens used. Right, you've already invested a lot. Exactly. So they had to build systems specifically to handle this. Systems that can resume from where the agent left off after an error. And even more, systems where the agent's own intelligence can try to adapt to failures, like if a tool temporarily breaks. It's a mix of AI adaptability and more traditional safeguards like retry logic and saving progress regularly.
Resilience by design. What about debugging? If these things are non-deterministic, taking different paths each time, debugging must be a nightmare.
It is definitely harder than traditional software. You can't always just reproduce the exact same bug easily. They found that full production tracing was absolutely essential. Logging everything the agent does, thinks, decides. That helps diagnose problems like why it chose a bad search query or picked a poor source. But it goes beyond just standard logging. They also monitor higher-level things like patterns in agent decisions again, while being super careful about user privacy, of course.
And deployment, getting new versions out there safely.
That needs real care, too, because you've got this complex web, right? Prompts, tools, the execution logic, all interacting. And it's highly stateful. You can't just stop everything and deploy a new version if agents are mid-task for users. So they use techniques like rainbow deployments. Basically, you roll out the newer version gradually, slowly shift traffic over, ensuring that ongoing agent processes aren't disrupted. It's like a soft landing for the new code.
Makes sense for long-running processes.
Yeah. And one more challenge they mentioned. Synchronous execution creates bottlenecks. Currently, in their system, the lead agent often waits for all the sub-agents to finish their tasks before moving on. That simplifies the coordination, it's easier to manage, but it also blocks the flow of information. The lead can't easily steer a sub-agent that's going off track mid-task, and the whole system can get held up if one sub-agent is slow.
So asynchronous communication would be faster?
Potentially much faster, allowing for even greater parallelism, but, as they acknowledge, it also adds a whole new layer of complexity to coordinate everything. That's likely a future direction.
Okay, so the big takeaway for building these things seems to be expect the unexpected. Design for resilience, design for observability, and understand that the gap between a cool prototype and a reliable production system is often much wider with agents.
That sums it up well, but despite all those challenges engineering, evaluation of these multi-agent systems have genuinely proven to be incredibly valuable, especially for those complex, open-ended research tasks.
And you can see that impact in the user feedback they shared, right? People using it to find business opportunities, figure out complicated healthcare stuff, solve tricky technical bugs, even saving days of work just by finding connections in research that they wouldn't have spotted alone. That's pretty powerful stuff.
Yeah, and it's interesting to see the breakdown of how people are actually using the research feature now. The top categories are things like developing software systems, that's about 10%, creating professional or technical content, that's 8%, business growth strategies, also 8%, academic research support is 7%, and just general research and verifying info is 5%. So quite a mix of complex knowledge work.
It really points to the potential here. So wrapping up our deep dive today, it feels like building these reliable, scalable, multi-agent systems isn't just about one thing. It's this combination of careful engineering, really thorough testing, super detailed prompt and tool design, robust operations, and probably deep collaboration between different teams.
Couldn't agree more. It takes all of those pieces working together. And maybe one final thought, connecting back to some of their other insights. For these really complex, long-running tasks, maybe the focus shouldn't always be on judging every single tiny step the AI takes. Sometimes it's more about Did it achieve the right final outcome? Did it get the job done effectively? And also this idea, like in good human teams, that sometimes enabling more direct communication between specialized agents rather than forcing everything through one central coordinator can be way more efficient, faster, better results.
That's a great point, focusing on the outcome and efficient collaboration. So here's a final thought for you, the listener. If collective intelligence is what made humans so capable, and now we're seeing AI learn how to organize its own form of collective intelligence, what does that mean for how you might approach solving problems? What kind of questions could you ask? What frontiers could you explore when information isn't just something you search for, but something that can be actively, intelligently, and collaboratively explored by a team of AI agents? Something to think about.